In astrophysics and radio astronomy, a digital down converter isolates faint cosmic signals buried in vast bandwidths of noise. Telescopes capture radio waves spanning hundreds of megahertz or even gigahertz, but the DDC lets scientists tune in to just the narrow frequency where something extraordinary happens, like the whisper of a hydrogen line and a molecular signature, or the unique tone of an interstellar object. So imagine you're staring into the universe, listening to a wide ocean of frequencies, 1,000 signals, all arriving at once from the stars. This is denoted as your incoming science signal bandwidth. Somewhere in that ocean, buried deep in the noise, there's one frequency, just one, that matters. So let's make this real. You're observing an interstellar visitor, Three-Eye Atlas, a mysterious object drifting between the stars. Its light, its reflection, maybe even its faint electromagnetic whisper carries thousands of frequencies. But you believe that one of them, one narrow tone, could be special. Maybe it's the resonance of a mineral that heals the body, or a harmonic that brings peace to the mind. To find that tone, we bring the universe into our receiver, a wide, roaring band of frequencies. And then we use a digital down converter to tune in. Then our ADC, the analog digital converter, begins to sample this signal, taking millions of snapshots every second. The continuous sky becomes a string of numbers. But in that moment, something beautiful and strange happens. The tone we want at plus F1 is joined by its mirror twin, minus F1. This reflection isn't a second signal. It's a mathematical echo born because our sampled data is real. Real signals are conjugate symmetric, meaning everything that happens at plus F1 also appears at minus F1. The ADC has created a digital mirror. Two tones, one positive, one negative, dancing in perfect symmetry around zero. In the frequency world, every time we sample, the entire spectrum replicates. Copies of the original bandwidth appears again and again, spaced by the sampling frequency Fs. Mixing. The problem. What is the problem? Your receiver sees everything. Gigahertz of information flooding in. You can't just look at one frequency. You have to extract it. The first step is called mixing. The mixer doesn't blend things, it shifts frequency. It's like playing a steady reference tone and listening to the beat it makes with the sound you want. The beat is slower, easier to hear, and that's what we can measure. In electronics, we do this by multiplying our signal with the pure local oscillator, basically a super steady sine wave we create on purpose. That multiplication produces new frequencies, one higher and one lower. The lower one is the beat, or our special signal, now sitting near 0 hertz, where it's easy to filter and study. Once our special signal is down to 0 hertz, or what we call baseband, we pass it through a low-pass filter to keep only the slow, gentle changes, the part that carries our note, our special signal. So mixing isn't about stirring things together. It's about translating a frequency to a new place where we can focus on it. It's how radios tune stations. It's how radar measures motion. And it's how we listen to the universe, one frequency at a time. So after we mix and use a low-pass filter to keep only the slow, gentle part of the signal, the frequency we actually care about, we can take the next step, downsampling. Here's the idea. Before filtering, we were taking snapshots of our signal really fast, maybe hundreds of millions of times per second, because we needed to capture every possible frequency in that huge band. But now, after filtering, most of those frequencies are gone. We're only keeping a tiny slice of the spectrum, maybe a few megahertz wide out of hundreds. So we don't need all those extra samples anymore. Downsampling just means we keep fewer snapshots, maybe one out of every 100 or 1,000. It's like you started filming a race with a super high-speed camera to catch every motion, but once you realize your runner is jogging slowly, you don't need 1,000,000 frames per second. Fewer samples equals less data equals easier processing. So now, I invite you to hit subscribe, hit like, leave a comment like where you're from, and stay tuned for our next video, which will be a MATLAB experiential learning example.